Hello and welcome back everybody. We started our section on the spectrum finally, but we haven't stated the major definitions yet. Instead we are currently preparing two little helpers. The first one we already proved. This was this statement that if you have a bounded linear operator on a Hilbert space which happens to be normal, so that simply means it commutes with its adjoint, then you can make the following statement. If you have Tx is equal to lambda of x for some lambda in f and some vector x in your Hilbert space, then the adjoint satisfies a similar equation, the only difference being here that the lambda comes with a complex conjugate on top. The x stays the same. That's the first helper. The second helper that I wrote at the end of the last video is this one. Again, you have a normal operator on a Hilbert space, and if you have two vectors x and y as well as two scalars lambda and mu that satisfy this equation and that equation, and the scalars happen to be different from one another, then these two vectors x and y have to be orthogonal. Alright, so let's quickly prove this, and then once this is done, then we will define all the important notions that come with the spectrum of a bounded linear operator. Right, so if t of x is equal to lambda x and t of y equal to mu y, then by the previous lemma, so the one that I just summarized one more time, then we have that t star x is equal to lambda bar x. You have a similar equation for the one with the y, so t star y is equal to mu bar y, but actually, that one actually we won't need, or actually if I look here in my notes right now, they tell me I use the one with y, but I don't use the one with x. Okay, fine. Both of them are correct. Mu bar y. Alright, and thus, this is a one-line computation now, so let's look at lambda inner product x with y. So, now, the inner product is linear in the first vector, so this would allow me to move the lambda inside. Alright, then in the first vector I would have lambda x inner product with y. But lambda x is t of x. That's one of the two equations that we have up there. Alright, so you have t of x comma y. Now you use the fact that you can move the t to the other vector, but you have to write the adjoint. So you got t star y. And now you realize why I want the equation for y instead of x. Well, this is then equal to x mu bar y. And you can also pull out scalars from the second vector in the inner product. However, then you have to put a complex conjugate on top. Yeah, but there's already one in there, so complex conjugate of the complex conjugate, they go out. Right? So what comes out here really is mu x y. Okay, let's move this a little bit to the left. Right, so we have this equation. So now what you should look at is this left-hand side in green equal to this right-hand side. You can bring both quantities to one side. Then you would have lambda minus mu multiplied by the inner product x comma y is equal to 0. The scalar 0, right? So, but since you have the left-hand side already factored, that can only happen if at least one of the factors is equal to 0. But the first one, the difference, lambda minus mu, is not going to be 0, because that's precisely what you assume up there, that lambda and mu are distinct. Right? So that leaves only one possibility, namely that the second factor, which is precisely the inner product x comma y, is equal to 0, and that's what's written up there. Alright? This yields the claim. Alright, so we have this. That we will use later on. Alright, so for now, enough preparation. Now we will state the major two definitions of this section. And well, here they are. So we are in a Banach space. This will be the minimal assumption throughout. We are no longer concerned with normed linear spaces at this point, and I will tell you why. So let's have at least a Banach space, and Banach space either over real or complex number field, and bounded linear operator on it. Now a scalar, a number, lambda in F, is said to be in the resolvent set that I will denote with rho of t. So in this lecture the symbol rho was used now for two things. Rho was used for the metric, which most of the time results about metric spaces. They were in the introductory chapter, which I didn't cover here in the videos because this material is supposed to be covered in the metric space module. We only used a metric, well, twice, I would say. It was in the Bayer category theorem that was formulated in complete metric spaces, and then there was this important corollary to the Bayer category theorem. There we also used the letter rho or the symbol rho for the metric. Now here this rho has nothing to do with a metric, but it will be clear this rho here only has one entry, namely t, not two x comma y, right? So rho of t will always be here the resolvent set. It shouldn't create any confusion, right? So we say a scalar is in that set if this operator lambda minus it is invertible, right? The invertibility here, because we are in a Banach space, because we have the inverse mapping theorem, that's the reason why we work in a Banach space here, is equivalent to the bijectivity of lambda I minus t, right? Remember, t is bounded, identity is bounded, so invertibility here is equivalent to the bijectivity. I don't need to check in addition whether my inverse is bounded because of the inverse mapping theorem. That's the reason why we want to have a Banach space up there, right? Good. If that operator lambda minus it is invertible, equivalently, if lambda is in the resolvent set, then this operator, which is just the inverse of it, it gets its own symbol, r sub lambda of t. It's called the resolvent of t. All right. So there's the resolvent set, and well, maybe I should also put the set here in red. So this up here is a set. The one down there is the resolvent operator. All right. If on the other hand you are not, if lambda is not in the resolvent, then lambda is said to be in the spectrum, sigma t. That's the abbreviation. So in other words, the spectrum sigma of t is simply the complement of the resolvent set in the underlying scalar field. That's the spectrum. All right, so you partition your scalar field in two things. There's the resolvent on one hand, where lambda I minus t is invertible, and then there's the rest where it's not invertible, and that's what we call the spectrum. All right, good. So these are the first two things: resolvent, resolvent set, and spectrum. Now, as I already summarized in words, if lambda is in the spectrum, that means this guy is not invertible, and since we're always working here over complete normed linear spaces, aka Banach spaces, then at least one of these two statements here must be true. Either lambda I minus t is not injective. This is precisely what this first statement says. The kernel, because t is linear and identity is linear, the kernel is not just a zero subspace. So this says lambda I minus t not injective. And the one here on the right, that's probably obvious, this says lambda I minus t not surjective, right? And these are the only two possibilities because of inverse mapping theorem and because we are in the Banach space, right? So operator is not invertible if it is not bijective. And that means either injectivity fails, surjectivity fails, or both can fail, right? But that's what's written there. At least one of them has to fail. Okay, good. Now we will distinguish further, and that now this definition, this is one of the most important one in the entire class, in the entire module, and it shows you a clear distinction between the theory that you learn about eigenvalues, eigenvectors in linear algebra, and now here the theory for infinite dimensional spaces. Right, so but let's start. Let T be a bounded linear operator on a Banach space. And now, first case. A non-zero vector that satisfies, well, the familiar equation Tx equal to lambda x is called an eigenvector of T with eigenvalue lambda in the underlying scalar field. All right, so this is the exact same definition that you remember from linear algebra, eigenvector, eigenvalue pair. So non-zero vectors such that T of x is a multiple of that same x and the multiple is the eigenvalue. All right. If lambda is an eigenvalue of T, note then of course lambda I minus T is not injective, because this equation here is of course the same as lambda I minus T x equal to 0, and the requirement that x is an eigenvector and lambda the corresponding eigenvalue just says that this equation up there in yellow has a non-zero solution, right? A non-zero x, and that in turn means that this operator here out front is not injective. Okay, good. So if lambda is an eigenvalue, then lambda I minus T is not injective, and thus lambda must be in the spectrum, right? So the eigenvalues certainly are contained in the spectrum, right? Remember this up here. You are on the spectrum if at least one of these two guys fails. Lambda I minus T not injective or lambda I minus T not surjective. And if you have an eigenvalue, then lambda I minus T is not injective. All right? So you're certainly in the spectrum. The set of all eigenvalues, this is what we will call the point spectrum of T, and it gets its own symbol. So we will write it as sigma T and then a little subscript P for point spectrum. Okay? Good. So these are eigenvalues, eigenvectors, and the eigenvalues all put together, they form the point spectrum of a bounded linear operator here on the Banach space. And if you were to do a class in linear algebra, that's where the train stops, because that point spectrum captures everything, right? And this is simply because in finite dimensional vector spaces, operators are injective, linear operators are injective if and only if they are surjective. But here, in infinite dimensions, that's just not true. So there is more to it, okay? That's why number 2. So if lambda is not an eigenvalue, that simply means lambda I minus T is injective. Well, then now the surjectivity must fail, right? And that's precisely what's written here in 2 and in 3. Range is not equal to x. That means lambda I minus T not surjective, but the range is dense in x. That can happen, all right? It might not be all of it. It might not be all of x up front, but if you adjoin all the limit points to that, then it might be all of x, and that's precisely what we summarize here in the second point. So range being dense. If that happens, then lambda is said to be in the continuous spectrum of T. Again, it gets its own symbol, sigma subscript C for continuous of T. All right. However, there could be another case, and that's the third one. If lambda is not an eigenvalue, so lambda I minus T is still injective, and lambda I minus T is not dense in X, then certainly it's not gonna be surjective. Then we say it is in the residual spectrum of T, denoted sigma sub R for residual of T. So the residual spectrum, whatever is left, right? So notice these 3 points there, the point spectrum, the continuous spectrum, and the residual spectrum, they partition your spectrum sigma of T disjointly, right? Because in the first one, you're concerned about those values where lambda I minus T is not injective. This is the eigenvalue stuff. And then in 2 and 3, you stay away from those guys, and then you partition the rest in 2 further subsets. One where the range is dense, and the other one where the range is not dense. That simply is it, okay? As I said, by definition, we have this disjoint union here, this one, okay? One has to be a bit careful if you look into the literature. All the books, they agree on the notion of spectrum and resolvent. This everyone defines the same. But then there are slight differences in the way one partitions the spectrum. Again, the eigenvalues, everyone uses the exact same definition, but some text sources, they choose a different partition of the rest, okay? So what they might call continuous spectrum might not coincide with what we call continuous spectrum. So just be careful if you read other textbooks about this. But we will stick to this, okay? Point spectrum, continuous spectrum, and residual spectrum. Okay, good. Let's do an example. All right. So at the moment we have nothing else besides this definition. So that example that we're going to do now, this will require quite some work. But then once the example is done, then we will start developing more theory and then realize that actually, you know, having that theory, this example is not so hard. All right. So, but let's do it now from first principles. So let's look at square summable sequences over f equal to c. So here in this business, the underlying scalar field matters a little bit. So in a formulation of a problem, one always has to write over what field we are doing this. With the right shift r. So remember this guy, it takes a sequence and just moves the starting entry 1 unit to the right and inserts a 0 in the first entry, right? And we have studied that guy early on in the first week. We know the operator norm is 1, okay? So now the goal, as usual in these problems, is to figure out the resolvent set, the spectrum, and then compute the point spectrum, the continuous spectrum, and the residual spectrum. That's a typical setup. Now there is no, unfortunately, or fortunately, however, if you want to see it, there is no golden route in doing this. I typically start with the point spectrum. Not always, but most of the time, and then make my way, you know, from there on. So let's do this here. So let's first look at eigenvalues. So first consider the eigenvector equation Rx equal to lambda x, with x being an element in L2. So now you have to write this out explicitly. I say entry-wise. Maybe let's do it in yellow and then erase that work. So R of x. So I have a left-hand side and I have a right-hand side. So I look at this entry-wise now. So on the left-hand side, I will have 0, x1, x2, x3, so on and so forth. And this has to be equal to lambda and then x1, x2, x3, so on and so forth, right? And this equality means that the corresponding components have to be the same. So you compare, right? First one here with first one there, second one here with second one there, so on and so forth, right? So doing this, now I will erase this, you get the following equations. So entry-wise, the first one, 0 is equal to lambda x1, and then all subsequent ones, xk minus 1 is equal to lambda xk. 4k, 2, 3, 4, so on and so forth. Okay, so now I will erase this yellow stuff. That's how you get it. Okay, so now this has to hold true, and I claim which tells us, for the first one, that's the easiest one. So in order to satisfy the first one, you can have, for instance, lambda is equal to 0. Yeah, but if lambda is equal to 0, and then the second one will tell you that the xk minus 1 are 0 for all k in above 2, so but these are all the xk, so then x would be equal to 0, and that's not what is allowed for an eigenvector, right? Eigenvectors have to be non-zero, okay? So that possibility you're not going to follow any further. So now let's assume that lambda is different from 0, but x1 is equal to 0. Yeah, but if x1 is equal to 0, and then from the second equation you get x2 is equal to lambda x1 is equal to 0, right? And then you go one step further, then you get x3 is lambda x2 is also equal to 0, so on and so forth. So again you get x is equal to 0, right? So this means simply that, there are no eigenvectors, eigenvalues, right? Because the eigenvalue-eigenvector equation is only solvable for x equal to 0, and that's forbidden. Okay, good. Which tells us x equal to 0. In short, let's erase this. In short, the point spectrum of the right shift is empty. Okay, no eigenvalues, no eigenvectors. Okay, well, but there's more to it, right? So next, with the operator norm equal to 1 and the Neumann series, so that we discussed in chapter 3, this is the geometric series for operators on Banach spaces, and the Neumann series, we obtain that, so we're interested in always lambda I minus r, so I will write this as lambda 1 minus lambda minus 1r, just pull out the lambda. So now the Neumann series, I claim, tells me is invertible for all lambda via over the complex number field here that are outside the unit disk. And why is this? Well, remember the Neumann series was this statement. So 1 minus t inverse is 1 plus not 0, 1 infinity to n, and here if the operator norm of t is less than 1. Okay, so now what I do is I identify this as t. All right, so and what is then the operator norm here? Well, it is simply, so norms are homogeneous, so 1 over lambda, and the operator norm of r is equal to 1, right? That we know from the right shift. So this I want to be strictly then 1, and that's precisely what's written up here, right? So the Neumann series guarantees that lambda I minus r is invertible if lambda is outside the unit disk. Okay, that makes sense. So this is Neumann series. Let's erase it. And consequently, so this means that the spectrum, remember that's the complement of the resolvent, well, it has to be in this complement, right? All right, and this is precisely the closed unit ball, right? Let's draw a picture here. So what I figured out through using the Neumann series, I figured out when lambda in complex modulus is bigger than 1, so all outside here, then lambda I minus r is invertible. And that consequently means the spectrum has to be a subset of, well, the closed unit disk, right? I'm not saying that the spectrum is the closed unit disk. I'm just saying it is a subset. That's important. The Neumann series is not an if and only if, very much like the geometric series. The Neumann series just says if the operator norm is strictly less than 1, then you have invertibility. It is not invertibility yields operator norm less than 1, right? That's why here you only have this subset inclusion. Okay? Good, so we have this. So this is some partial information. Here the notation, I think I've used this before, so dr z naught, this is z and z with z minus z naught less than r. Okay, good. So now we have this, all right? But now I claim, and I will prove it, but lambda I minus r is in fact non-invertible on all of d10. In other words, this subset inclusion up there is actually an equality, but that does not follow from the Neumann series. Indeed, it follows from this argument. For if lambda is equal to 0, then let's look at this element here. So this is an element in L2. This is just the vector 1, 0, 0, everything else 0 except for the first entry. This is not in the range of lambda I minus r. If lambda is equal to 0, right? And why is this? Because then this range is just the range of r. And remember, r is the right shift. It moves everything one unit to the right and inserts a 0 in the first entry, right? But this vector here has a non-zero entry in the first entry, so it cannot be in the range of r, right? So that means it is not surjective, right? So lambda equals to 0 is certainly in the spectrum, and if 0, the complex modulus is away from 0, then lambda I minus Rx equals to 1, 0, 0, 0 has no solution. Has no solution x in L2n. Let's see. Okay, this is my last claim for this video. I will explain why this is the case in the next video. It's simply you have to write out the action of r, and then you will be able to solve this explicitly, and you will realize that x is not square summable. Yeah, that's fine. Okay, so I will stop here. We will complete this example in the next video, and then once done, then we will start building theory that will make our life easier in the future. All right, I'll see you then.